In 2011, a towering tsunami struck Japan, killing more than 20,000 people and erasing hundreds of thousands of homes in minutes, leaving the world stunned. That unimaginable loss pushed the nation toward an unprecedented response. A colossal tsunami defense wall stretching nearly 250 miles along the eastern coast. To raise barriers approaching 50 feet high, capable of resisting millions of tons of water, Japan mobilized tens of thousands of engineers, machines, and construction methods measured to the millimeter. Yet one question still hangs over it all. Can this concrete wall shield Japan from future tsunamis? Let's find out. But before we continue, hit subscribe for more unbelievable engineering. Why Japan drew a concrete line against the sea. For decades, Japan's northeastern coast has lived under a threat the entire world fears: the lethal pairing of earthquakes and tsunamis. The country sits atop the meeting point of four massive tectonic plates, a restless collision zone where the earth constantly grinds, slips, and unleashes more than 500 earthquakes each year. When those plates suddenly shift beneath the ocean floor, the seabed can rise or sink in seconds, forcing enormous walls of water upward and sending tsunami waves racing toward shore with the weight of millions of tons. For generations, coastal towns learned to listen for red alert sirens and run uphill the instant the ground began to shake. But March 11, 2011, proved how fragile that routine truly was. A magnitude 9.0 earthquake tore open more than 300 miles of plate boundary beneath the Pacific, spawning a tsunami nearly 50 feet high, far beyond anything Japan had prepared for. The wave erased over 20,000 lives, crushed more than 120,000 homes, and sparked a catastrophic crisis at the Fukushima nuclear power plant. Seawalls built to stop waves of just 26 feet were swallowed whole. Japan realized the earthquake was only the opening act. The tsunami was the real destroyer. In response, the nation constructed nearly 250 miles of tsunami defense walls, rising 45 to 50 feet tall, anchored by foundations plunging 80 feet deep. This concrete Great Wall was designed to buy precious evacuation minutes. More than $12 billion also strengthened alerts and escape routes. The message endured forever. The first step toward Japan's massive tsunami wall began far from the coast, inside research labs. Engineers gathered every data point from the 2011 disaster, then rebuilt the waves in giant tanks using scaled models. Again and again, water slammed, climbed, and spilled over the walls. Each test forced changes: greater height, thicker concrete, sloped faces, and deeper foundations to stop collapse when waves surged past the top. Only after endless trials did one design prevail: a 14 to 15 meter wall with foundations driven 20 to 25 meters deep, reinforced. Once the final design was approved, the next challenge was deciding exactly where this massive barrier would rise. The nearly 400-kilometer stretch follows the Tohoku coastline in northeastern Japan, the region that absorbed the full force of the 2011 tsunami. It runs through Aomori, Iwate, Miyagi, and Fukushima, forming the longest coastal defense line in Japanese history. After the route was finalized, crews cleared the area, removing old homes, damaged infrastructure, power lines, and pipelines. At the same time, access roads, material yards, crane platforms, concrete mixing stations, and drainage systems were built so work could continue during the rainy season. Much of the Tohoku coast rests on weak, sandy soil, so engineers conducted detailed surveys and reinforced the ground. Deep concrete and steel piles were installed. Crushed stone and compacted sand were added, and the surface stabilized. The mission was to create a foundation strong enough to support a wall tens of meters tall without sinking, sliding, or cracking. Once the soil was secured, excavators dug enormous foundation pits, some extending more than 20 meters deep. Near the shoreline, crews built temporary retaining walls and cofferdams to keep seawater out. A thick concrete base was poured, followed by dense steel reinforcement cages and massive foundation blocks, forming a wide footing designed to resist waves. Above this base, workers assembled tall rebar cages based on optimized laboratory designs. Formwork was set, and concrete was poured section by section. Each block, often several dozen meters long, was poured, cured, inspected, and connected, creating one continuous barrier along the coast. On the ocean-facing side, crews installed specialized concrete units such as tetrapods, dolos, and other energy-dissipating blocks. Stacked in multiple layers, they broke wave energy before impact. Some sections featured stepped faces, sloped surfaces, or splash reduction ledges to reduce surges. On the landward side, soil and crushed rock were added, along with drainage channels to prevent rainwater buildup. Many sections included walkways or inspection roads, and in some towns the seawall became part of the local roadway. Railings, fences, ladders, and signage allowed public access. This description reflects the general construction method across the project. Because the wall spans nearly 400 kilometers, each area required small adjustments based on terrain, soil, and coastal depth. These variations did not alter the overall design of the tsunami barrier. In sections requiring extra thickness and impact resistance, crews added precast concrete panels to the outer surface. Lifted into place by cranes and arranged in uniform patterns, these blocks formed a reinforced armor layer that reduced erosion and helped the wall withstand decades of Pacific waves. In busy port cities such as Iwaki, engineers designed special access points to keep ships moving. One solution was a top-down tsunami gate using a massive steel panel suspended between concrete towers. When a warning is issued, the panel drops from above, sealing the harbor. Other ports rely on bottom-up rising gates. Normally resting on the seafloor, these gates lift during a tsunami, locking into sidewalls to block incoming water. Built with corrosion-resistant steel and sealed hinges, they endure constant pressure while allowing uninterrupted marine traffic. Every stage demanded precision coordination, constant inspection, and strict adherence to safety standards throughout. And that's how Japan's massive tsunami wall came to life. Stretching nearly 400 kilometers along the Tohoku coastline, it is the largest continuous coastal defense system the country has ever built. The project cost over $12 billion, mobilized more than 30,000 engineers, workers, and geotechnical specialists, and kept thousands of heavy-duty machines operating non-stop for 5 to 7 years. Hundreds of wall sections were constructed simultaneously, each requiring unique foundation treatments, concrete structures, and reinforcements tailored to local terrain. Once complete, simulations revealed the new seawall could reduce tsunami impact forces by 30 to 50%, buying precious extra minutes for evacuation, enough to save tens of thousands of lives in a level 1 tsunami. Coastal roads, fishing ports, and residential areas that were once vulnerable are now far better protected, drastically lowering the risk of catastrophic damage. While it can't stop every tsunami, this monumental barrier represents Japan's final line of defense, giving the nation confidence against one of the planet's most devastating natural threats. What do you think? Can a wall this massive truly stop a tsunami? Share your thoughts in the comments. Don't leave just yet. Beneath Japan's coastal waters lies another engineering achievement just as astonishing as its tsunami defenses. In a world sealed off from air and light, under crushing pressure and constantly shifting geology, Japan's underwater tunnel technology stands as a powerful symbol of human resolve against the sea. Every completed tunnel reflects the nation's engineering skill, discipline, and refusal to be limited by nature's extremes. In today's interconnected world, underwater tunnels are no longer optional marvels. They are essential arteries of modern transportation, and Japan ranks among the global leaders in this field. These submerged structures link islands, cross deep bays, and unlock new routes where bridges or ferries can no longer meet rising demand. Because of them, travel between coastal regions is faster, safer, and no longer dictated by storms or rough seas. Goods and commuters move steadily through busy port cities, turning these tunnels into economic lifelines that strengthen competitiveness and open doors to long-term development. But building a tunnel beneath the sea is never straightforward. Success begins long before construction, with meticulous planning and near-perfect design precision. Engineers must first understand the hidden world below. Detailed seabed surveys mark the starting line. Teams map underwater terrain, extract soil samples, and analyze rock layers to assess geological structure, load-bearing capacity, and unseen hazards that could threaten stability. At the same time, environmental responsibility remains central to every decision. Project teams carefully evaluate potential impacts on marine ecosystems, ensuring wildlife is protected and habitats are disturbed as little as possible. Noise reduction methods are introduced during construction, and in some areas artificial reefs are installed, transforming disruption into opportunity by creating new marine habitats. Once surveys are complete, construction begins using one of the most proven techniques available, the immersed tube method. Massive reinforced concrete segments are fabricated on land, each stretching roughly 217 meters and weighing more than 73,000 tons. Built with extreme precision, these sections are designed to align flawlessly and seal tightly against water intrusion. Inside each segment, space is carefully divided. Two main chambers carry highway traffic, another accommodates rail lines, and a dedicated service corridor allows future inspection and maintenance. When ready, the completed segments are transported offshore and gently lowered into pre-dredged trenches using floating pontoons and specialized cranes. Segment by segment, the tunnel takes shape. The most critical stage lies at the joints. Even minor sealing errors could allow seawater to enter, risking catastrophic failure. To prevent this, rubber gaskets are installed between sections to ensure watertight connections. Sand and gravel are layered above and around the tunnel to counter buoyancy and stabilize it against water pressure. Only after every connection is secured are temporary bulkheads removed, transforming separate elements into a continuous, sealed passage. Still, this method has limits. It works best in areas with stable seabeds and mild currents. In turbulent waters or complex geology, anchoring and waterproofing become too risky. Completion does not mark the end. Safety inspections and operational testing follow, with many tunnels designed on 2 levels to double capacity without increasing size. Vehicles move steadily at about 60 kilometers per hour, while emergency exits appear every 200 meters. Even after opening, vigilance never stops. Maintenance defines longevity. Teams regularly inspect linings, membranes, supports, and drainage systems. Hundreds of sensors track pressure, temperature, humidity, and vibration, sending constant data to control centers. Cleaning vehicles remove sediment to prevent blockages. Through precision engineering and relentless care, these underwater tunnels endure for decades, standing as quiet monuments to human resilience beneath the sea. Final horizon. You've just seen how Japan shapes ocean-facing giants, from towering tsunami walls to deep undersea tunnels. These feats reveal not only advanced engineering, but a nation that rises stronger after disaster. Subscribe for more global mega projects and comment below with what amazed you most today now.